Okay, so this is the video for 5.6 polynomial equations with complex and radical roots. The objective is I understand why radical or complex roots are in conjugate pairs and can write a polynomial equation when given roots of the function. So first we need to jump back to complex numbers for a second and go over some things that we've actually learned before. So with complex numbers, remember a complex number is written a plus or minus bi. It always has the real component followed by the imaginary component to make a complex number, which again has both parts, a real and an imaginary. And then the other thing we need to remember with complex numbers is how the i's work. So the square root of -1 is I. Therefore, if we square both sides, -1 equals I squared. So when we go through and we do the multiplication for A, B, and C, we have to remember at the very end that we need to swap that I squared out for -1. And then also we need our answers to be written as a complex number with the real part followed by the imaginary part. So when I look at A, B, and C, those are all multiplication. I am multiplying a binomial times a binomial, so we need to FOIL that first, outside, inside, last. Be careful on these, but again, I know you've seen these recently. So all you need to go through and do is first, outside, inside, last. Then we do have like terms in the middle that I'm going to combine in the next step. And the last thing I'm going to do in this step is make sure that I swap that I squared out for -1. So if I have -15 times -1, it's like plus 15. Now I have like terms one more time, and I want to write my real component first. So the answer is going to be 17 minus I. Then we can look at this next one. Again, we need to FOIL it out. 8 plus 12i minus 12i minus 18i squared. Again, I squared is equal to -1, and we do need to combine these like terms. So I'm going to go ahead and do that. 8, and then I have 12i minus 12i, so those actually are going to go to 0 because they're opposites. And then I'm going to change this to plus 18 because, again, if you subtract 18 and it's being multiplied by -1, it's like you're adding 18. So then we have like terms again, both real components, so we can add those up to get 26. Sometimes, if you notice in this one, you will multiply complex numbers together and you don't end up with a complex number. Sometimes when you multiply the right complex numbers together, you end up with just a real number. That is an example of how that would happen. So go ahead, try to do C. I am going to move pretty fast through this video because, again, it's a video. At any point, you can pause the video if you need me to go slower. All right, so on that last one, again, we're going to FOIL one more time. I get 4 plus 8i minus 8i minus 16i squared. Again, we have like terms here and they're opposites once again, so that imaginary component is going to go away. And then I need to deal with this I squared by making it -1. So I'm going to have 4 plus 16 to get 20 overall. So once again, a situation where I multiplied two complex numbers together and the product ended up being real. Very interesting. Okay, so this is also review, but I do want to throw it back to the last time we saw radical roots and complex roots, and that was in our quadratics unit right before we went to winter break. So when did they show up? You can, again, pause the video and think about when that happened, but if you don't remember, really when we've seen that in the past is with the quadratic formula. The quadratic formula was what we used when we had really, really messy solutions to a quadratic because you get messy solutions when you really can't factor, you can't square root, and you either have to complete the square or do the quadratic formula. So those, again, are the situations where we prefer the quadratic formula because if it's going to get messy, it's nice to put it into a formula and just work on simplifying from there. So let's take a look at these two examples, and we're going to solve them with the quadratic formula. If you want to be out of the box and do completing the square, by all means, go for it. But since they're both in standard form and set equal to 0, I think quadratic formula would be the way to go. And they're quadratics, right? So that's why we could use the quadratic formula on these. So I have A equals 1, B equals -8, C equals 41. I'm sure everybody has the quadratic formula memorized still, but go ahead and plug into the quadratic formula and then see if you simplify the way that I do. So again, I have opposite of B plus or minus the square root of B in parentheses squared minus 4 times A times C all over 2A. Then I like to go through and simplify sections at a time. So I like to simplify B squared, and I like to simplify 4AC all over 2. Then I can simplify what's under the radical. So I get the square root of -100 all over 2. Then we have to deal with the radical. So again, the square root of -100, that includes the square root of -1 and the square root of 100. So when I split that up, I'm going to get I from the square root of -1, and then I'm going to get 10, so I guess that would be 10I all over 2. And then you do have to think about this in sections. So the 8 over 2 can reduce because they're real numbers. 8 over 2 is 4 over 1. And then the 10 and the 2 can reduce. They're both even. So the solutions on this, I'm going to split them up. X equals 4 plus 5I. Again, I just divided the 8 by 2 and the 10I by 2. And then that was the kind of positive route with the plus sign. And then X equals 4 minus 5I as the second solution. So again, 2 solutions to this quadratic. These are both complex solutions, and what I want you to pay attention to is how are those solutions related? So they have a couple things in common. That's really something we're going to be talking about today when we introduce conjugates, but keep that in mind. Okay, so my audio cut out, so I'm now doing a voiceover on this part. But anyway, we are going to solve this again with the quadratic formula. Find A, B, and C. Opposite of B plus or minus the square root of B squared minus 4AC all over 2A. Again, don't simplify too much at a time. So I'm just going to simplify -4 quantity squared. Remember, you are squaring a negative, so it turns positive. Then I would end up with plus 8 all over 2. Then we're going to go through and simplify what's under the radical to get the square root of 24. And you do need to remember with radicals, if there is a perfect square stuck in it, you need to take that perfect square out. So 24 can be broken into the square root of 4 and the square root of 6. And then from the square root of 4, I'm going to pull a 2 out front. So I will end up with 4 plus or minus 2 root 6 all over 2. Then you do need to simplify the first part. So 4 over 2 is going to reduce to positive 2. 2 over 2 will reduce to 1. And you have to account for the plus and minus. So one of my solutions on this is going to be 2 plus 1 root 6, or you can just have that as root 6. And then the other solution is going to be 2 minus 1 root 6. I think I forgot to write x equals, so I'm adding that back in and doing the same thing on this one. So x equals 2 minus 1 root 6. So if you noticed on those two examples, those solutions are related in that the real part matches and the complex part or radical part is opposite. And so that goes with today's key concept. Anytime a polynomial function has a complex or a radical root, it is part of a conjugate pair. And again, all that means is you can't have a complex or radical root if it's not in a pair because of the plus or minus from the quadratic formula. So that's how we end up with them. And let's look at some examples to see how these work. Okay, so again, these are just pairs of conjugates. So the real part's the same. It's positive 2 in both. And then the radical part is positive and negative because of where the plus or minus would be in the quadratic formula. So at the end of the quadratic formula, you would have ended up with 2 plus or minus root 3, which is how we get those conjugates. Now the next one I think is a little bit more tricky, square root of 5 and negative square root of 5, because the real component of that would have been 0. So it would have been 0 plus or minus square root of 5. Same thing on the last one. The real part is the same. It's negative 3 on both. And at the end of the quadratic formula, that would have looked like negative 3 plus or minus 2 square root of 5. We can also look at these for complex roots because they also come in conjugate pairs from the same idea. Again, you can't get a radical without taking the square root of something. You can't get a complex number without taking the square root of something. So if we look at the complex ones, again, that first pair is an example where the real component would have been 0. So 0 plus or minus 3i. That's how I end up with positive 3i and negative 3i. Again, I suggest looking and thinking, how would this have looked at the end of the quadratic formula? If you want to get really fancy, the real end of the quadratic formula would have been 0 plus or minus the square root of negative 9, because again, that is how we get 3i. So practice working backwards if you're at that stage. Same thing for the next one. It would have been 2 plus or minus 4i. That's why the 2 doesn't change, but the I part does. And then on the last one, negative 3 plus or minus I root 2. Again, the same idea. Imagine what it would look like at the end of the quadratic formula. And if you can imagine what it looks like when the radical was still negative, that's another really good thing to practice. So in the next section, it says, for each of the following, find the other root that would complete the conjugate pair. Again, a root is a solution. So that is a situation where you'd have x equals that when you are solving with the quadratic formula. But what we want to do is practice making sure we can find the other part of the root. So again, imagine what would this have looked like at the end of the quadratic formula, and how could I find the conjugate pair? So if we look at the first one, 2 minus the square root of 13. You need to imagine what that would look like at the end of the quadratic formula. So it would have been 2 plus or minus square root of 13. So the missing piece is 2 plus square root 13. On the next one, to get 3i as a solution, you would have had to have 0 plus or minus 3i. So since we have positive 3i, going out of control there, we end up with negative 3i as the other solution. I'm just writing it out again. I really want you to imagine what that looks like at the end of the quadratic formula, because that makes conjugates much, much easier. If I ended up with the square root of 23, that would have been 0 plus or minus the square root of 23, so we're missing the negative part. There it is again. And then to get 1 minus 2i as a solution, that would have been 1 plus or minus 2i at the end of the quadratic formula, so we are missing 1 plus 2i, which again, I am writing in pink very diligently. So try to do that second column and then see if you agree with me here in a second. Okay, so here's where I ended up. E was 6i, F was 1 minus root 5, G was negative 6i, H was root of 7. Again, you can also imagine this. It's the same format for complex numbers, A plus or minus BI, or A plus or minus square root of B for the radical conjugates. So again, the real part stays, the complex or the radical part is what changes. Now we are going to tie this into what we've been doing with roots and factors and going from factored form to standard form. Okay, so we're supposed to find a polynomial in standard form of least degree and a leading coefficient of 1, which has the following roots. So first things first, remember, real roots do not come in pairs. So if I have negative 5 as a root, I only have that one time. We've seen that before. It's totally allowed to have x plus 5 as a root with a multiplicity of 1. It's the complex root that we need to worry about, and we have to get its conjugate pair. So if one of the conjugates is negative 6i, again, imagine 0 plus or minus 6i. The positive 6i is something that we would also need. So those are roots. We now need to convert them to factors. We're assuming that a is equal to 1, which is nice. So remember, you take x minus your root, and when I'm taking subtraction of a negative, it turns to positive, which is how I ended up with x plus 5 as the root in parentheses. Then I have to do the same thing with each complex root, so I'm going to subtract 6i. Again, I showed it with parentheses so that we don't forget to change the sign. And then I need to do the same thing for the second one, so x minus 6i. Now, you also want to remember that when you have conjugate factors, those are the ones that you want to multiply first. So now I have my conjugate factors written out. I simplified them with the parentheses so that we're ready to go. And we will be foiling those conjugate factors first because, again, a lot of stuff is going to eliminate. So by the time that we multiply out those conjugate factors, our i's should be completely gone, and we will have a much simpler polynomial from there. So first gets me x squared, outside gets me negative 6ix, inside gets me positive 6ix. Those are opposites, so we'll go away, getting rid of some of the i's. And then we have negative 36i squared. Again, that I squared, we are going to change to negative 1 here in a second. So x plus 5 is still hanging out in front. And then because of that I squared, I can change that second factor to be x squared plus 36. Now I have a much easier situation to FOIL and get to standard form. So I'm going to FOIL one more time. The way that I ended up doing this, the outside term was linear, the inside term was quadratic. So the answer I have in this step's actually not in standard form. But you'll see I take one more step to put it into standard form. You want all of these in standard form, meaning any quadratic factors should happen before linear factors. Again, you always want your highest degree first. So the answer on this is y equals x to the third plus 5x squared plus 36x plus 180. All right, so now we're going to do example number 2. The nice thing about example number 2 is we are only given one root, but we do need to find its conjugate pair. So 2 minus root 7, 2 plus root 7 would be the conjugate. And you need to remember, these are binomial roots. So these are roots that have two parts to the solution. So when we write these as a factor, what you end up having is x minus the root, but you have to subtract that as a binomial. So look how I write this out. This is a place that I see mistakes. I'm going to have x minus the quantity of 2 minus root 7. That means I need to see how the subtraction is going to work on the 2 and on the negative root 7 separately. Okay, so don't forget that when you plug that in, you should plug that in parentheses because you're going to then have to distribute that negative before you FOIL things out. I have to do the same thing on the second conjugate root. That should be a 7. There we go. And then again, I will distribute that negative. So now we can go through, we can write out what the roots look like when they're simplified. Again, once I have subtracted that binomial in each factor, so I end up with x minus 2 plus square root of 7, x minus 2 minus square root of 7. Now I can completely FOIL it out. They do each have 3 components, so that's going to be a little bit messy. But again, in the end, since we're multiplying conjugates, they end up being so much nicer. So I get y equals, we're going to go through each term, x squared minus 2x minus x root 7. Then we do the kind of inside term, so negative 2x plus 4 plus 2 root 7. Then one last time, plus x root 7 minus 2 root 7 minus 7. Again, the square root of 7 times the square root of 7 just gets me 7. Now look how nice things cancel. We have a few opposites. So we're going to get rid of negative x root 7 and positive x root 7. We can also get rid of 2 root 7 and negative 2 root 7. Again, they're all opposites, so they go to 0. Now I only have a few linear terms, a few constants that need combined, and I will be to my final answer. So I get y equals x squared minus 4x minus 3. Again, as a quadratic, it does not look bad at all, but we do know how messy those roots are. They're radical roots, they're conjugate roots, but the quadratic itself looks really nice because, again, no i's or radicals in that standard form. All right, so now we're going to move on to example number 3. In example number 3, we still have a real root, and it has a multiplicity of 2 this time, so we'll get to see how that works. And then we also have 3i that needs its conjugate pair. Okay, so again, with 3i, for that to be a conjugate, I would need 0 plus or minus 3i. So I can go ahead and write out the conjugate as negative 3i. Then I can use that information to go to factors. Sorry, I got an email, ignore that. So I have y equals x plus 1 is the factor that goes with the root of negative 1, and I have the multiplicity as 2, but since I'm going to standard form, I'm starting by just writing them next to each other. That's going to make it easier to FOIL down the line. Now, these complex roots are monomials, so when we subtract, we don't have to worry as much about subtracting a binomial like on example number 2. So I'm going to get x minus 3i and x plus 3i. Now, you want to make sure you're multiplying the conjugates together first because, again, they're going to end up nice. And you can also multiply x plus 1 and x plus 1 at the same time to save yourself a little bit of multiplication. So when I FOIL out those first 2 factors, I get x squared plus x plus 1. When I multiply out those second factors, I get x squared plus 3ix minus 3ix. Those are going to go away. That's why we don't have any i's in our final standard form, minus 9i squared. So again, I suggest simplifying these by combining like terms, getting rid of your imaginary stuff, and then after that, we will distribute one last time. So I get y equals x squared plus 2x plus 1, and then x squared plus 9 as that second factor. So again, that one simplifies way nice if you do it correctly. So I'm replacing I squared with negative 1 to get plus 9 at the end. Now we need to do one more round of distribution. Distribute that x squared, distribute that 2x, distribute that 1. I know it's tedious, but it's not particularly difficult, which is nice. So I end up with x to the 4th plus 9x squared plus 2x to the 3rd plus 18x plus x squared plus 9. And then I do have some common, like terms that can be combined. So x to the 4th, it looks like I have 2x to the 3rd, 9x to the 2nd, 10x to the 2nd plus 18x plus 9. All right, so that's it. Use the answer key if you need to go back and refer to anything and work on your homework for the rest of the hour. I'm happy to answer questions when I see you guys on Wednesday.